Sure. Hello, welcome everybody. I'm Court Brinkerhoff, the project manager for PSR, and I'm going to go ahead and introduce our panel moderator, who will introduce the panel session and the presenters. So our moderator today is Jeanie Ward-Waller. She is the Deputy Director of Planning and Modal Programs at Caltrans, and she is also a PSR Advisory Council member. So thank you, Jeanie, for moderating, and I'll turn it over to you.
Thank you so much, Court. Hi, everyone. Excited to be with you this afternoon. We've got a really exciting panel. This is a session that includes 3 different presentations on the theme of technology to address transportation problems and improve mobility. And we're going to talk about mobility both for passenger and freight travel. Our first speaker is Yiqiao Li, who is a Ph.D. candidate from UC Irvine. And each of the presentations is going to go about 10 minutes, and then we'll have time for Q&A at the end. So I think you can put your questions in the Q&A box, and we'll try to get to them at that portion at the end. Yiqiao, I'll turn it over to you.
Yiqiao, just a note, you'll need to turn on your camera and mic one more time. Great, we can see and hear you, so all of you go ahead and start presenting.
Okay, just a really quick test. Are you able to hear me?
Yes, there does appear to be some background noise, but we can hear you.
Really quick, I will close the window. Sorry about that. Okay, then I will get started. Today I'm going to present our work related to truck body type classification using representation learning algorithm on a 3D point sets. Right, can we go to next slide? Okay, as you may know, that truck have different impacts on economy, freight planning, and emissions. Based on the data from Bureau Transportation Statistics, we know that truck accounts for approximately 8 to 9% of GDP in US from 2010 to 2018, where trucks were the primary contributor to account for almost 80 to 90% across all modes. And based on the prediction results, we know that from freight analysis framework up to 2014, the total value moved by truck could potentially reach up to $18,000 per ton. And the most important thing is the truck have adverse impacts on the emission. For example, particularly for heavy duty truck, it contributes over 50% of the pollutants, such as all the pollutant emissions listed below, down below. And knowing those issues, what we should do is we need more data to have a better understanding of our current commercial truck travels, right? So what type of data we need? We need the industry-related, industry-affiliated truck classification data, because we ultimately want to know where the commodity, what type of vehicle is traveling across which corridor, right? And also we want to expand the spatial coverage of civilian area, right? Because, for example, we not only want to have a better understanding on the major highway, we also want to care about the rural highways. Also, we need to know the indication of those duty classification, for example, light duty truck, medium duty truck, and heavy duty truck, so that those information can be used as an input for the emission model. And our solution that we proposed for this study is we want to use a LiDAR-based truck classification, truck body type classification. We want to develop a LiDAR-based truck body type classification model. Yeah, let's go to next slide. So here is our data collection setup. We conduct our study at Southern California San Onofre truck scale. The San Onofre truck scale is along I-5 freeway, and this detection site is near the county line between San Diego and Orange County. And we collect over 7 days data in 2019 at July. And as you can see, in this detection site, we equipped a video camera for ground truth purpose. Can you play this? This is a video, so can you play the video? Yeah, there's a video. Right. As you can see, this is what you can see in the video camera. And we also have a 32 beam array LiDAR to capture the 3D point clouds of the ambient environment. And we synchronize these two. We synchronize those sensors together to manually ground truth the point cloud data. But in previous study, we used inductive loop signature data to do truck body type classification. So we use that as a platform to semi-automated label and doing manually correction for our ground truth data set. Overall, we collect 9,000 vehicle point clouds for our model development. Can we go to next slide? Okay, so here comes the data pre-processing part. As you may know, that point cloud data is a huge data set. So before we do truck classification, we have to eliminate some of the background noises to accelerate our data processing and the modeling process. So the basic idea is, as you may see in the previous slides, there's a lot of background related to our roadway conditions. We don't really need for the modeling for the classification purpose. So the first step is extracting the foreground vehicle point cloud from the background roadway environment. And after that, we have to identify whether this is a truck or this is or just a random noise. So we use a density-based clustering method called dbScan to group those vehicle point clouds so that we can identify, for example, in the second picture, the green one is the vehicle 1 and the yellow one is vehicle 2. After doing this, across multiple frames, we have to identify the same truck, those frames are associated with the same truck. The technique we were using is data association. And we combine the Hungary algorithm and the common filter to do a real-time tracking to make sure that all the frames belonging to the same truck. So we assign the multiple frame to a same folder to make sure that they belonging to the same certain trucks. Can we go to next slide? So after doing that, we find those single frame of a truck is not is too sparse to identify some of the key feature to differentiate a certain type of truck. Like you can see, you may see on the road a 53 feet container and 53 feet enclosed one. They're quite similar with each other. The only difference probably based on visual verification, we know the corrugation on the boxes. That could be the only difference between those two trucks. So we need more details. So how could we get those information? So we merge multiple merge the truck point cloud across multiple frames. The first step we did is we did a pairwise registration. As you may see in the first picture, the yellow one and the blue one, they are consecutive frames, and we apply a transformation matrix from the yellow one to to the blue one, so that these two frames can closely align with each other. After getting the transformation matrix across multiple frames, we constrain this transformation matrix to the ground plane, because the basic assumption all the tracks should be landing on the ground, right? And this is really beneficial for other track classification scheme like FHWA axle-based classification scheme, which define their classes based on the number of axles touching the ground. Right, so this could be really beneficial step for other classification scheme. The final step is we fine-tune all the transformation matrix using a global optimization algorithm to finally tighten up the alignment across multiple frames. This is what you can see in the GIF. So ultimately, we get the overall reconstructed. This is a 50, maybe 40-foot container, and the class 10 40-foot container. So can we go to next slide? So here is our reconstruction results across different type of trucks. The first one is a single unit platform truck, right? The second one is a 53-foot container, and as you may see in the single frame, it's really hard to observe their tandem axle on the trailer part, but for the reconstructed one, you can clearly see that this is a 5-axle semi-trailer truck, right? But especially for the last one, the tank truck, for the single frame results, you may see you may find this is this type of truck looks like a dump truck or maybe a tank truck. But for after reconstructed, you will find this is really a tank truck with a tank trailer. So this is this showing the benefits coming from the truck reconstruction framework. Can we go to next slide? After getting those reconstructed point cloud, we get the overall view of this truck, right? So we have to classify them. Before using the predictive model, the predictive model we are using is a neural network representation learning algorithm, a neural network model. So to meet the needs for the neural network model, we do a downsample. We downsample them to 1024 points, and then normalize them to a unit sphere to accomplish the normalization process. Can we go to next slide? The algorithm that we choose to use is called PointNet. It's a deep representation learning algorithm, which is different from the classic machine learning algorithm. Classic machine learning algorithm is you're trying to accomplish a classification task. What you do is first you extract the key features to identify different classes, to differentiate different classes. But for representation learning algorithm, it is an end-to-end learning algorithm. You just get the raw point cloud through into the neural network model, let the neural network model to identify the key feature that will be used for the classification purpose, and finally getting the final results. On the left-hand side, you can see is the PointNet architecture. And here, we didn't use just a single one PointNet for making decision. We use an ensemble model. Ensemble model, there are two different strategies we apply for our applications. One is simple model averaging, one is Bayesian model averaging. The ensemble model is basically we no longer making decision based on one single model. We're making decision based on the prediction score across all 5 different models. So the two strategy we are using, the simple moving average is just averaging all the prediction score across 5 different models. But for Bayesian model averaging, we're taking a weight on certain model which previously have a pretty good prediction results on certain type of classes, and we think it did a really good job for the previous model. It should do a better job for the future. So we give a more weight to consider their prediction results. So this is the model structure that we use for our classification purpose. Can we go to next slide? Here is our prediction results. Here I list 5 different PointNet model and their prediction accuracy. The really good example is the first row. Different model predict 20 feet containers in different have a different performance, but after we assemble the model, we find the prediction result, prediction performance increased, right? So here we compare the simple model and sample averaging method and the Bayesian method. You can find that the Bayesian method is slightly higher than the simple method, but based on we did assigned statistical test on that. Based on the statistics test, there is no significant difference. So we will give suggestion that you use either of them is good enough for your prediction purpose. And on the right-hand side is the 30 different type of truck that we are able to correctly classify. And you can see we are able to classify tank truck, the end dump truck, and for example, we are able to distinguish 53 feet containers from the 53 feet enclosed one, which serve different, which may carry total different commodities and show up in different strategic freight corridors, right? So here is the overall our presentations. Can we go to the next slide? And finally, I would like to introduce our team members for this LiDAR research. And if you have any questions, please let me know or shoot me an email. Here's my email address.
Thank you so much, Yiqiao. That was fascinating.
Thank you.
Really impressive study. With that, I want to keep us moving so we can try to stay on time and have time for questions. I'll introduce the next speaker. It's Sue Dexter, who is a PhD candidate at USC. Sue, go ahead.
Thank you so much. I hope you can hear me okay. I am going to be talking to you about a project done in Southeast Los Angeles about studying freight. I come from USC, and my particular area of focus is sustainable urban freight. Next slide, thank you. So Southeast Los Angeles, if you're familiar with the LA area, you can see that the city of Los Angeles is at the top there at the north, and the Long Beach port is at the very bottom. And the 710 freeway runs right here in the middle, and there's all these other major freeways that take port traffic and other containerized traffic through the area. So there is about 14 to 20,000 trucks per day that is visiting the port, both inbound and outbound. A lot of this traffic goes through this area. So a project that's headed by Dr. Giuliano was done in conjunction with the Sella Collaborative to reduce health and environmental impacts of freight activity in the area. And there was a focus group that was held very early on in the project. And what we found from that focus group is that the residents in the area were more concerned about the safety aspects of trucks over the pollution aspect. So we added this into the project program to address those particular concerns. Next slide. Very quickly from the demographics, although it is very, has a lot of industry and warehousing in the area, which you could basically see, this is the population density. So that would be in the light yellow areas is where that is. And the darker areas would be mainly residential, and then the middle, the light brown areas would be mixed use areas, pretty much, as we would overlay the land use type of things. But we can see that you know, there is quite a lot of population density in this area, being that it is very close to the LA area. So next slide, please. 86% of the population is actually Hispanic and Latino in this area as well. So when to collect data on the freight accidents, there is a database, and it's called the Statewide Integrated Traffic Record System, and UC Berkeley actually has this database of all of the accidents reported. And it is accumulated by the California Highway Patrol for both highway and non-highway. And so we utilize 4 years from 2015 through 2018. And then this is geolocational data, so we could map it. So you can see here that there is, the stars are the fatal accidents, and then where pedestrians are involved, also crashes at intersection, which you can see as a whole lot. And then there are multiple accidents that occur. Unfortunately, this is hard to show on such a small map, and some of the things are very overlaid on each other because of the fact that there are crashes at the same location. As far as looking at hotspots, you can basically see that at the very lower quadrant here at the very bottom, that would be Rancho Dominguez. It is mainly distribution centers and those kinds of things, so there is a lot of crashes there. And also along the Alameda Corridor here and near the freeways. So one of the things to note is we know that not every single accident is reported, but probably all the severe ones are. So, and also I've hidden all the freeway crashes for this particular study because this was a residential focus. But the street accidents for trucks, heavy duty trucks, is about 55% of the total in this area. Next screen. Thank you. So what's the cause of these accidents? Well, speed and lane changes are 50% of the problem. So you have a truck that's going pretty fast over their speed limit. You know that they take longer to slow down and stop too. And then also the time of day was very interesting to us, that we found out that, you know, 26% actually happen in the hours when kids are getting out of school. So this was actually something that was said in this focus group. You know, the kids that are walking to and from school, they're walking on these major streets that have a lot of freight traffic in it. So some other things too, you know, comparing to LA, which is right next door to it, the accidents or the crashes are twice as great as in that particular adjoining area, with a lot denser traffic, which was pretty unexpected. Fatal accidents in the area are higher than the surrounding zones as well, by 1%. But the data also confirmed that the crashes happen during the week when there is more truck traffic than on the weekends. That was 82% of the crashes happen during the week. Next slide. Thank you. So this is drilling down into the data, and we looked at those particular accidents that were fatal, and then also those which were injury related. So you can see, thank goodness, that it's very small on the part of the fatalities, but unfortunately, there's an average of 4 people killed per year and 127 injured per year in this area on these non-highway areas. Although pedestrians are only 6% of the total, they made up 38% of the fatal accidents. So, you know, there's not much protection walking when you're walking or crossing an intersection and a truck and you're in an accident with a truck, you're not going to win. So over the total of these 4 years, we found that 5% were severe visible injuries, 26% were other visible injuries, and 69% were complaint of injury. And these were all recorded by the law enforcement officer that took down the report. So this is something that might be a little bit subjective, unless it was a severe accident, and then that's probably those particular people did go to the hospital. Next slide. So what we did with this information is with a team of other USC students, Robert Binder and Marley Randazzo, we overlaid the crash data with information on land use and also truck traffic volume to really identify those particular areas that we were interested in going and looking with our own eyes to see what was going on. And so we were really interested when we did this. You can see that the darker rose colors, areas of melon colors with the red dots, were the areas that really popped. Can you do the overlay, Court? Thank you. So you can see that there were 6 areas that were identified in these that correspond also with that map that we looked at before, to go and actually, look at. So we did go and analyze the traffic and pedestrian flows, the truck behavior, and the built environment around it. Next slide. I have a couple of examples here of what we found, and this was more by happenstance. I was actually looking at the road, the big road next to the Alameda Corridor that's right here to the right of this area that's shaded. And the red area that's highlighted in the map is this particular stretch in front of a corning plant. And you can see on either side of the corning plant and also to the left is all residential areas. So you have this plant right in the middle, this heavy industrial plant right in the middle of this residential area. But we did see a lot of dangerous activity on the Alameda Corridor, and I'm only going to touch on just a few things here. Some of the things that we saw is we saw trucks gun it to make lights and to make aggressive turns that were dangerously close to oncoming traffic. Also to note that buildings are built all the way to the sidewalk, making visibility practically impossible for turning. And in one stretch of the corridor, the street is split into 2 with the Alameda train corridor in the middle, which has a lot of problems with backing up of traffic because of the synchronization of the lights, and also a metro train station which blocks traffic as well. So there's a lot of things going on. This actually is in Tamarin, and we found that there was a lot of trucks who were just parked, double parked, triple parked on this particular stretch of road, idling. And I hung around for over 30 minutes and they didn't move, and they were on. So investigation we need to do further is to determine why the trucks are congregating there, and for extended time periods, and are there other areas like this? When we did ask the focus group later on, we did find out that yes, there are other places like this in the area. So there, we need to find out why they're not going to another central location to when they're waiting for pickups or deliveries or those kinds of things. So some of the recommendations that we're making for these types of things are enforcing idling restrictions, because there are laws on the books that trucks need to turn off the engines while they're not moving, and also implementing geofencing to keep heavy duty trucks off of residential streets in this area. Next slide, please. Also, very quickly, another area that we looked at was this flyover. Now, this is a Rosecrans flyover all over the Alameda Street, and both Alameda and the Rosecrans corridor are heavy truck traffic volume corridors, but you can't turn from one onto the other. So this makes it very problematic. So what happens is especially if trucks that are heading eastbound, which would be coming from the port areas or other warehousing areas near here, going to Hobart or other places, they'll turn right before Rosecrans and go into the pure residential areas. So we were wondering why that there was accidents in these places, and that is is why, because there's trucks in very small stop line ridden streets where they definitely shouldn't be. So we have some recommendations, you know, for signal timing and also geofencing for these areas as well. Next slide. We're putting together the report right now, which has the full recommendations, so that will be available soon. Thank you.
Thank you so much, Sue. Also really fascinating study. Appreciate that work as well and the recommendations. So our third speaker is David Lemcke. He's an undergraduate research assistant at Northern Arizona University. And I'll just remind folks, as David's talking, please put your questions, if you have any, for all three of our speakers. Please put them in the Q&A. David, I'll pass it to you.
All right, thank you. Can you hear me okay?
Yeah.
All right, great. Hello, everyone. My name is David Lemcke, and today I'll be presenting on examining the use of microsimulation modeling to assess bicycle vehicle conflicts at signalized intersections. Next slide, please. Okay, so in this study, VSIM microsimulation software, along with SSAM, or the Surrogate Safety Assessment Model, were used to identify and extract bicycle vehicle conflicts from a simulation model based on surrogate safety parameters, which were post-encroachment time and time to collision. PET, or post-encroachment time, indicates the extent two road users missed each other in a near-miss circumstance, and time to collision is the time until collision between vehicles, which would occur if they continued at their present rates and courses, like speeding courses. So the advantage of using surrogate measures of safety to assess safety at intersections is that you can more easily examine the safety impacts of traffic characteristics and road user behavior without relying on police-reported crash data, which is sometimes lacking for bicycle vehicle conflicts. Yes. So this study performed a quantitative analysis on how driving behavior parameters impact the frequency of bicycle vehicle conflicts in microsimulation. This was done to understand the steps and procedures required to calibrate microsimulation models to field observed bicycle vehicle conflicts. Next slide, please. All right, so the microsimulation model used in this study was based on the signalized intersection of West Butler Avenue and South Beaver Street here in Flagstaff, Arizona, with the focus being on the southbound approach. This approach was chosen because of its standard bicycle lane treatment, where the bike lane moves away from the curb to the inside of the right turn pocket. A single camera collected 7 hours of video footage, and this was used to recreate the user interactions in VSIM and to identify field-observed bicycle vehicle conflicts. And figure 2 here shows the example of the camera angle used in this study. And I myself went through and watched all the vehicles and counted their movements, and then I also went through and identified the conflicts. Next slide, please. So figure 3 identifies the type of bicycle vehicle conflicts that was the study of this, or the focus of this analysis. Figure 4 provides an example of post-encroachment time. As you can see, one vehicle is like leaving the conflict area and the next vehicle enters it. And the time that elapsed between that is the post-encroachment time. And figure 5 shows 3 different examples of bicycle vehicle conflicts that we observed in our video data. Next slide, please. So once the VSIM model had been created with the geometry, signal timing, and vehicle movements that we observed, the simulated bike vehicle conflicts were ready to be collected. For this study, the baseline model was ran 10 times with all the default settings and with 10 different random seed values. The random seed in VSIM directly influences the arrival of vehicles, traffic flow, and stochastic function. So depending on your random seed value, it will change how vehicles arrive and kind of change how things interact. So we decided to use, for each of our different treatments, 10 different random seed values to make sure that even if the patterns change, that the results we saw were consistent. So several time to collision thresholds were used in this study or tested. As you can see, we used a threshold of 1.5 seconds, 2 seconds, 2.5, and 3 seconds. And those could be adjusted in the SSAN software. And the post-encroachment time was kept at 5 seconds, the threshold. From our research, our literature review, that was the standard time used. Then, once all that was set in stone, the behavior parameters outlined in Table 1 were changed one at a time from their default values and also ran 10 times. And combinations of promising parameters were also tested. And the resulting effects on conflict frequency and operational performance were summarized for each treatment. And it should be noted that we used values both greater and smaller than the default value. And from the video footage, we saw 25 bicycle vehicle conflicts. So that was the target that we were looking for in our models. We wanted to see if the models were able to recreate those interactions. Next slide, please. So Table 2 outlines all the different driving behavior combinations used in this study. These were created by combining the parameters that had the greatest impact on conflicts. So we would look at the different parameters we tested, and the ones that produced the most conflicts we chose, and we would put them all into one model and then run it to see which combination was the best. Next slide, please. It was determined that the time to collision threshold of 3 seconds was most appropriate for bicycle vehicle conflicts because it gave results that were closest to what we observed in the field. As the time to collision threshold increased, the conflicts observed in the models or that were identified by SSAM increased. And the most influential parameter was the average standstill distance, which defines the distance between two users. Table 3 shows the results of two different parameters, the additive part of safety distance, or APSD, and average, or ASD. And those outline some of the values we used. And the results, the average from the 10 simulation runs we did, that's the average number of bicycle vehicles that were identified by SSAM. So it was determined that combinations of parameters had a significant impact on bicycle vehicle conflicts, and the random seed value also had a significant impact on the number of conflicts. Next slide, please. These two figures, figure 6 and 7, show the bicycle vehicle conflicts for the baseline model and combination 4, which was one of our most successful combinations. It gave us some of the most conflicts that we saw. And it should be noted that the random seed value of 50 consistently saw more conflicts than other random seed values across all treatments. The highest number of simulated bicycle vehicle conflicts occurred in the random seed value 50 at time to collision 3 seconds, and it's circled in red for figure 7. And this showed us that the random seed value had a big effect with this relatively small number of bicycles at this study. And depending on what the random seed number is, it would have a big impact on how many bicycle vehicle conflicts the SSAM identified. 22 is very close to the 25 conflicts we saw in the field. Next slide, please. So for conclusions, this study demonstrated that the default driving behavior parameters within VSUM underestimate bicycle vehicle conflicts, because we saw 25 conflicts from our field data, or the video, and the baseline model only reported an average of 9 conflicts. This study also demonstrated that changing driving behavior parameters individually and in combination impact the frequency of bicycle vehicle conflicts, with the average standstill distance parameter having the largest impact. Further research is needed to understand how to recreate bicycle vehicle conflicts consistently and accurately, regardless of the random seed value. Future research should focus on intersections with similar geometry to the ones studied in this experiment, but with varying and higher volumes of bicyclists. This could increase the chances of bicycle vehicle interactions and provide insights as to a possible threshold of bicycle vehicle volumes where, above that amount, the random seed has a minimal impact on conflicts. And finally, our lessons learned in this project are being applied to our current project which focuses on understanding the safety viability of several different bike treatments in Portland, Oregon, including bike boxes, mixing zones, and bike signals, as seen in Figure 8. So we're continually trying to find out how to use VSIM to accurately replicate bicycle vehicle interactions in our current project. And next slide, please. And that concludes my presentation. Thank you so much.
Thank you so much, David. We are just about at the scheduled time for the end of this session. So I just want to check, Court, how much time do we have for questions, or are we going to have to wrap up without questions?
I think we can go for hopefully another 5 to 10 minutes.
A couple minutes? Okay. All right, great. Well, I will I'll ask all the panelists to go ahead and come back on camera, so I'm not just looking at myself. And I'll ask for folks in the audience to go ahead and enter your questions if you have any in the Q&A box. And I'm seeing some comments pop up in the chat, so thank you. But if you have questions, feel free to enter them. Maybe I will kick off the discussion just by thanking each of you. You know, from the perspective of a state DOT, I think all of your studies add significantly to the data-driven tools that we need to make decisions from a transportation agency perspective. And we're sort of constantly looking for ways to be more sophisticated in understanding where there are conflicts, also understanding where the context of the community is being impacted. So Sue, your conclusions about neighborhoods, residential adjacent to industrial areas where there are trucks idling and, this high risk of crashes, I think is really just very valuable. I wondered if each of you could maybe just reflect a little bit on how your study is scalable. Because of course, the Department of Transportation, we're thinking about doing corridor planning. We're also thinking about trying to tackle these issues on a statewide level. So I wonder if you just have thoughts on, the scale of the study that you did either at an intersection, or Yiqiao, yours was at a specific, location where you're measuring the LiDAR data. How might you scale that, and how scalable is your study at a bigger level?
Well, I definitely can take a stab at it, because I do think that the data that's available is it's accessible for anybody to utilize it. And so any city could actually study for their particular, geography level, since it is a geolocational data as well. So I'm thinking that, to be able to see, especially for those particular pockets with hotspots in them, it's pretty easy to do. So I would hope that when we are able to present this data to the cities themselves, that they can, take the ball and run with it. Of course, they're in charge of making the changes to their street structures and light changes and all of that. We can only say here's the issues, here's some things we have recommendations for, but it's the cities that need to move forward the ball. Anyway, I know that there's another question for me, but I'll leave that until afterwards.
Thank you, Sue. That's very helpful. David or Yiqiao, go ahead.
Yeah. I'm really excited about my work. I love riding my bike, and anything that makes bicycling more safe is something I'm very interested in. And our current research is really interesting because we're analyzing 3 different treatments, like the bike box, the mixing zone, and the bike signal. And we're going to see, with varying amounts of volumes, which one performs better in certain circumstances. And I think that could be useful possibly in the future. You could look at your intersection and say, oh, we have this many vehicles, maybe a bike signal, maybe a bike box is better. And anything to improve the safety, any way that we can help that, I think is very important.
For my study, for now, we are just focusing on the rural highway because there's the limitation for LiDAR sensor is occlusion. But based on our registration algorithm, we could somehow address the occlusion issue in some way. And we haven't proved that, but we will collect more data to prove that it can be applied for multi-lane highway. But probably, but based on my experience, it's a little bit hard to extend to maybe 8-lane or even more. But the beneficial for LiDAR sensor is a mobile sensor you can deploy at the rural highway, which the pavement condition may not be preferable for those intrusive sensors. So it's filling the gap there. For current study, but we are looking forward to explore more the ability of LiDAR sensor, how this can be applied for a multi-line highway, and extend our work. It's really exciting.
Excellent. Thank you, all three of you. Sue, I've got a question for you that came through on the Q&A. Has geofencing as you proposed been used for this purpose before?
That's a great question, and I haven't read, especially from a residential perspective, where it has been used. But the way that the geofencing has been used in these areas is, especially in like low emission zones and those kinds of things, to track when and where and how often, you know, particular vehicles are going in and out of different areas, you know. But a lot of these tools are more at a firm level or at a service level provider level. You don't have it necessarily, you don't have the government tracking, you know, individual firms or trucks in these areas for, you know, reporting or for tickets or something like that. That's not being done, especially in California, of course, right? So as far as from an enforcement perspective, there is that, how do you take that into, you know, to the next step to say, is it adequate enough for firms to have their trucks with these particular, you know, devices on them? I mean, they have the GPS locational devices. It's pretty easy. And then being able to talk to them and retrain their drivers or why they shouldn't be going into there. But then, you know, the next level up is these, you know, consolidated organizations that have this data, and what would they do with it? You know, there's some issues with that, right? So, but I think that it's an excellent question, and I would need to do a little bit more research on that. But I know that we were thinking that what a great use of that technology to be able to provide this information.
Absolutely. Well, I don't see any other questions in the Q&A. Maybe I'll ask just one more and kind of invite you to close with that. But all of you talked about sort of, you know, the need for more study or ongoing study that you're already doing. And I think, you know, again, just reflecting from a practitioner in the field, you know, the growth that we anticipate in freight movement, you know, freight travel, goods movement demand, you know, is just going to continue to grow in the coming decades. And I think bicycling, I think of as a mode that we want to continue to grow, but there are a lot of, you know, inherent conflicts. So having, you know, this kind of data and using it to help us make decisions about investments in infrastructure is so valuable. So I just would love to invite you to sort of reflect on, you know, what are things that you would like to study more, you know, deeper study, or maybe some work that you're already doing that you could just in brief describe for us before we wrap. And any of you, please jump in.
Yeah, I already kind of mentioned how like my current research is focusing on like the different bike treatment. I'm just looking forward to finishing that, like kind of get some results from there. We're almost like we're making a lot of progress, and I'll be very interested to see like how the different treatments perform. And in the future, if there's anything else I can learn about bicycle safety or how to make bicycling more available, I think that'd be very good. I'm almost about to graduate, so I'm very excited to see what's out there and any way I can help to make bicycling a more viable option for people.
Well, having worked for a bicycle coalition, I always like to hear that too, that folks are excited.
Awesome.
Sue or Yiqiao, would either of you like to just talk about future study or things that you would have liked to dig into?
Well, I just think that it was, really interesting for us for this particular, we had in our mindsets that it was going to be the pollution impacts and people were going to talk about their children inhaling, fumes and those kinds of things. And then it was a 180 as far as what the concern was. So, the collaboration with the community and working with the community and finding out what was the most impactful for them really led us down this path, right? And so as far as for what I see myself is in the future is always going to the source. You can make your assumptions, you can make your plans, but if you don't check with the people who it's ultimately affecting and get direction from them, what's the use of that, right? So I think that it was a really powerful message to me. Don't go down that path so much. So that's kind of like a really high level overview, but from what I learned from it and how I'm going to take my research going forward, that's probably one of my #1 lessons.
That's fabulous, Sue. I commend you for the openness and for engaging in dialogue with the community to understand what would be most valuable. That's really.
That was all on Dr. Giuliano. I cannot take any credit for that whatsoever.
Excellent. Yiqiao?
For me, I'm currently working on develop FHWA axle-based classification model using LiDAR sensor. So conventionally, people can collect those data from weight in motion sensor, which is sparsely deployed across the network. So with a LiDAR sensor, which is a mobile sensor, we can put it everywhere, so that we can enrich our data set, have a better understanding of the track activities over the network. Also, we are also looking to integrating inductive loop signature data with the LiDAR sensor. So because the LiDAR data can give you lots of detailed information about the track, so how this information can be utilized to enhance the previous signature-based model. This is how the sensor interact with each other, how integrating those information together is mainly the path I'm looking into.
Wonderful. Well, thank you, all three of you, for your work and for this discussion. It's been really interesting, and I have certainly learned a lot. So appreciate all the time you've invested. I think from here we are going to a break. I might just ask Court if he has any instructions. If you want to jump on and let us know.
Yeah, we're going to take a quick break, and we'll meet back here in 5 minutes for the student awards presentations. So thank you all.
Thank you so much.